Okay, recorder, please take the floor. You have 12 minutes to present your work.
Hello everyone, I'm a reporter from Typt, and I'm going to report number 9 of oscillating school. Okay, this is our outline. This is problem 7. When placed on its side on run and release, a school may experience growing oscillations as it travels down the run. Okay, it's our result of observation. The inclined angle and the shape of the school affect the motion greatly. This is our discussion of parameter. The motion will affect by inclination angle, school shape, the mass of school, and temperature of the plane. And when we have moderate angles, the school will rotate quicker. And when we have higher angles, the school will slide downhill. Okay, this is our theory. We can think a school is similar to a cone, and the height is the school's length, and the R is the size of school's head. Okay, when the school rolling on the plane, we can see the school is oscillating with the OA, and you will have a angular velocity. We can know the rotational inertia is this, and kinetic energy is this. We can derive I, rotational inertia is this, and the motion of oscillating can be seen SHN motion. Okay, and we can know the period equal to this. It is the conclusion and prediction. The school on the plane's motion depends on the friction of the plane, and oscillation period depends on the phi, which is the inclined angle, and the period of oscillation also affected by the shape of school, its height and its size of head. And we can see the oscillations growth from kinetic energy. Okay, this is our first experiment. We change the inclined plane's angle. Okay, we put the screws on the top of the inclined plane and release it and observe its oscillating motion. And then change the 45 and 60 degrees of the inclined phase. This is our observation video. This is the 45 degrees of the inclined phase. And this is the 30 degrees of the phase. We can see the screw is start here and oscillating. Okay, this is our 30 degrees result. We can see the position theta is decreasing. It's decreasing with the time and ending in the stop. And this is the 45 degrees. We can see the position theta is not ending in the stop. And this is 60 degrees. We can see the position theta is increasing at first and be constant at the end. Okay, it's the second experiment. We use five type of screw. These 5. And we put these 5 screws on the plane and on 50 degrees angle and with P 240 centimeters. Okay, it is the longest screw. It's 1.5 centimeters. And this is a 1 centimeter screw. And this is the 0.75 centimeter. It's flipped here. And the bolt is 0.625 centimeter. And this is the 0.5 centimeter. You can see it flips at first. Okay, this is the 0.5 centimeter. And this is 5/8 centimeter. And this is 3/4 centimeter. We can see the speed idea here is special because it's flipped here. And it's 1 centimeter. And this is 1.5 centimeter. Okay, this is the chart we get. Okay, the third experiment is about the clock efficiency of friction. And we can see is the P100 and P240 and P800. We can see by changing inclined angles, each observer take a big part in affecting the motion. And the shape of screws also change the motion. And the friction coefficient is also affect the equation greatly. And this we can get large inclined angles will have shorter parallel, and longer screw will have longer parallel. Shorter screw and large angle will flip, and small friction coefficient will slide when in motion. And here is our reference. Thank you, everyone.
2 minutes for the opponent to propose questions.
First of all, what is the main reason for the oscillation of the screw?
Here are three.
Short answer, please.
Here are three reasons. The length of screw.
Okay. So the three different parameters in your report, right?
Yes.
Okay. Do you consider the thickness of the head of the screw?
We change the.
Did you consider in the theory?
Yes, there are our edge. Edge is.
Okay. Thank you. What are forces that acts on the screw?
Here are the friction and gravity.
And where do friction act on the screw?
When
Where?
the screw contact with the
Okay. And do you think the direction of velocity will be different on different contact points? The direction of velocity.
Yes, I think.
Okay. Do you think the magnitude of velocity will be different?
Yes.
And which one is bigger? Is the contact point with the head or the tail?
I think the tail is bigger.
Okay. And will the contact area of two contact points affect the phenomenon?
10 seconds.
Will the contact area of two contact points affect the phenomenon?
Yes.
Okay. Is the friction constant throughout the oscillation?
Yes. It also varies the oscillation.
And what is your releasing method in your experiments? How do you release a screw?
We use hand.
You use hands to release screw, right?
Yes.
Okay. And do you think the normal force will be bigger or smaller if the inclination angle increases?
I think when the angle increase, the normal force will decrease.
Okay. Do you believe that the rotational frequency will be different if you change different parameters?
Time is up.
Okay, thank you.
3 minutes for the opponent. Okay, opponent has maximum 4 minutes to take the floor, followed by discussion with reporter, for a total of 14 minutes.
Honorable juries and all the competitor, I'm the opponent from Team Celsius, opposing problem number 9, oscillating screw. This is a problem statement. When placed on the side on the ramp and released, a screw may experience growing oscillation as it travels down the ramp. Investigate how the motion of the screw, as well as the growth of these oscillations, depend on the ramp's parameters. So due to the problem statement, we mainly focus on the motion of the screw, also in which situation that the screw will experience growing oscillations, and relevant parameters that will affect the motion of the screw. So this is the outline of the reporter. So in the theory part, he assumed that the screw as a cone, and he calculated the angular velocity also using rotational inertia to calculate the period of oscillations. And in the experiment part, he changed 3 different parameters. First is about the inclination angle, which is increased. The angular acceleration will increase, and the shape of the screw and coefficient of friction. Also, he analyzed the angular change of the screw. However, I believe he lacked of in comparison with the theory, which didn't explain the deviation with the theory. These are the strong and weak points of the reporter. So he has a clear observation video, and he considered a lot of factors and he considered the length of the screw. However, he has an unclear explanation of the structure of the screw, because he assumed the screw as a cone. However, he didn't explain this and how he assumed and the reason for it. And he didn't mention how they consider the thread of the screw, since there are various threads on the body of the screw. And he lacked of explanation of which kind of friction acting on the screw, since there are static friction, kinetic friction, and rotational friction. And I believe he didn't calculate the boundary limits, since in his chart there are sometimes the oscillating angle will decrease, and sometimes it will increase, and it may be boundary limits of this phenomenon. So here are the points I'm going to discuss in the discussion. So in the first part, I'm going to discuss about the structure of the screw. The different structure will affect the rotational inertia of the screw. Since a reporter assumed it as a cone, I believe that it may cause a deviation when it's compared to external data. And I'm going to discuss the characteristic of the screw, and including the thickness of the head and the length of the screw. And also the screw thread, how will the radius of the screw affect the phenomenon? And also the forces that act on the contact point, which is friction. What kind of friction that acts on the contact point? And about kinetic friction, static friction, and rotational friction. And also different magnitudes of 2 different contact points. And in the experiments, I'm going to discuss the releasing method. Since the reporter use their hands to release the screw, I believe there's a better way to release the screw to cause and to reduce the experimental error. And I'm going to discuss 3 different parameters: releasing angle, inclination angle, and friction coefficient. And in this part, in the motion investigation, I'm going to discuss the trajectory of the screw. How will the overturning situation change the trajectory? And in the oscillation investigation part, I'm going to discuss the angular acceleration and the phenomenon of overturning. Overturning and well, let's be a boundary limits of this phenomenon. Thank you. So So you mentioned that there are three different parameters that will affect the oscillation. Can you explain about this?
Yes, in our experiments we change the inclined angle and the length of screw and the sandpaper.
Okay, I understand that. And can you explain why there's a kind of weird oscillating change in this part?
The screw here will have a maximum angle, and here is going to oscillate. So its angle is here. It's down and up.
Okay, so the screw will decrease the oscillating angle will decrease first and increase at the end. Is my explanation correct?
Yes.
And the reporter believed that this experimental error might be caused by because the reporter thinks he used a hands to release. However, this unstable situation here might caused by the experimental error, which he used the hands to release. Did you agree with my?
We use hands. Although we use hands to release it, but we do many experiments to decrease our experiment error.
So this is one of the experiments.
Yes.
Experimental error, right?
No, I think it is the result when it's oscillating. So I think it's not an error.
Then can you give me a basic explanation of this part?
Yes, because the screw is do SHF motion. So it's oscillating here, from here, and going to the middle.
Okay, I would like to skip to the next question. Since you assume the screw as a cone, I would like to discuss the structure of the screw.
Yes.
So here is a screw and also a cone. And you can find out that there's only one contact area by using a cone, and there's two contact points by using a screw. Did you agree with me?
Yes.
And do you think that one contact point and two contact points can affect experimental results and theory?
I think it will be the error come from it, but but the version of it is the same.
Okay. So, you think that the friction on contact points, this one and this one is the same?
If we place on an inclined plate, it will be different.
It will be different.
Yes, but if on the
Then,
plate, it will
if you assume it as a cone, the friction will be different, and the friction will be the same, right? If you assume it as a cone.
I think I cannot either because
So, do you think that the friction will be different on this point and this point of those?
yes, because your head of cone it has more weight, so
But it's the same contact area. Right?
yes, but it will have its top is has to be the same. So I think
I understand. And I believe that if the reporter assumes it as a cone, the friction will be the same in this contact area. However, if the actual screw like this, the contact points at point A and point B will be different, which is the error of the theory. Do you agree with that?
yes.
Okay, thank you. And I would like to discuss about the releasing method. Since you use hand, do you think there is a better way to release a screw?
I think if I can do better, I will use a stick to make the screw stop at the first and release the stick.
Then can you control the releasing angle if you use a stick?
It's as same as we use the hand. We make the screw from 90 from 90 degrees.
Okay, I understand that. However, I think using a stick could also cause an experimental error, because a stick might touch the screw and cause the experimental error. I believe using electromagnets on the bottom of the ramp, and then without magnetic force, the screw will oscillate downward. Do you agree with my reason? So do you think this is a better way to release the screw and cause a smaller experimental error?
I think if we do many experiments, we will get the results, and we can compare with this and to.
So how many experiments did you do with these parameters, like this one? How many experiments?
Yes, we did very much. We did very.
So this is the best one to show on the screen.
Yes.
Okay.
And the other experiment is also very similar to this.
Yes. Also very similar to this one.
Yes.
So this is a normal oscillation.
Yes.
Can you go to the next page?
Yes. Yeah.
Okay, I would like to go to the next question. And is there any boundary condition of this phenomenon of growing oscillation?
What is boundary?
Boundary, like there's a boundary limit that the screw may experience growing oscillation. Since the problem statement asks we to analyze the screw will grow, the oscillation will grow.
Yes.
However, the oscillation in your chart might also decrease, right?
Yes.
And is there any boundary limit, like how many inclination angle will the screw start to decrease?
It's related to the angle and
Do you think there is a boundary limit?
in our experiment we did 30 degrees, 45 degrees, and 60 degrees. Yes. But the limit is different from we use 1.5 centimeter and 1 centimeter.
And perhaps can you explain about the boundary limits of inclination angle? Only inclination angle.
If the angle is higher, it will decrease. The acceleration will decrease. Yes.
So if the angle is higher, the oscillating angle will decrease when the inclination angle goes up. And the opponents disagree with this part, since the inclination angle increase, the initial potential energy will increase too. And also the potential energy change by each oscillation will increase. So it will make a screw oscillating bigger, since it has more energy to consume. Do you agree with
But I think if the angle is large, you will slide down. It won't oscillate it.
But the potential energy is bigger.
But
And the energy will be constant through.
But the gravity is more bigger than
Yeah,
the other force.
may I use the blackboard, please? Thank you.
Next page.
You say that like this is a screw. So if the inclination angle increase, the gravity, vertical components of gravity will also increase, right?
Yes.
So the screw will experience a more bigger oscillating angle. Am I correct?
But if the gravity is larger, it will slide down.
Okay. The opponent disagree with this part, since the torque will be bigger if the torque of the oscillating angle will be bigger as the inclination angle increase, because it's the vertical components of the
Okay, time is up.
This stage.
1 minute. Opponent to conclude.
Honorable juries and other competitor, this is my discussion summary. So, in the first part, I discussed about the structure of the screw. Since the reporter believes it can be assumed by the screw, however, the opponent disagrees with this part because the contact point, the friction will be different on two different contact points. And I talked about how different forces act on the different parts. And I agree with the reporters that the friction acts on the contact points. And there's he did different parameters to affect the motion of the screw. And there's an unexpected peak in the experiment. I believe is caused by the releasing method of the reporter mentioned, which you can use a hand. And I suggest the reporter can use a better releasing method by using an electromagnet to release the screw. And I talk about the boundary condition of the motion. Thank you.
Reviewer has 3 minutes to ask questions before opponent the report.
For the opponent, can you please predict what will happen if we change the different weight of the head and tail of the screw?
Different weights of the head and tail of the screw.
Yeah, so
Yes, I understand. So the center of the mass will, if the head of the screw is bigger, the center of the mass will bias to this side, which causes a bigger angular acceleration. Because it's different from the center of the screw.
I need the weight, like not the mass of this. The weight of the head and tail, not the mass.
The weight.
Yes.
Yes, so the weight will be bigger and the center of the mass will bias to the head if the weight of the head is bigger.
Okay, thank you. Then can you please explain the difference between a screw and a cone?
Yes, and as I mentioned in the discussion, a cone, there is only one contact surface with the cone and the rim. However, there's two contact points with the cone and with the screw and the rim. So the friction will be different when two contact points. There are two contact points. And okay.
And for the reporter, do you think that your experiment is a part of a periodic motion?
Yes.
Okay, then can you please predict the motion if you add the width and the length of your surface? Because oftentimes in your video, your screw falls off the surface.
Oh yes. But in my experiment, we only to observe its motion. We don't.
So do you think that the video that you presented is only a part of the phenomenon of the experiment?
Yes, I think it's enough.
So if it's only a part of the phenomenon, can you please predict what will happen if you add an infinite length and width of your surface?
It will stop because the friction.
Okay, thank you. Can you please tell us how your experiment reflects on the formula of your inclined plane rolling cone? Because there's no
doing this.
Yes.
This is the phi, and this R and H. H is the length of the screw, and R
Okay, time is 3 minutes for using time for the review.
如果有我在一起。
Okay, the girl has 4 minutes to present her point of view.
Okay, hi, we're Team Meg, and today we're going to be reviewing the oscillating screw. So, in this discussion, we believe that there are 4 tasks that should be talked about. So firstly is to construct a reliable experimental setup with reproducible results. Secondly is to have qualitatively and quantitatively explanation of the phenomenon. Thirdly is to create a successful theory examining the motion of the screw when it's rolled down the surface. And lastly is to investigate the effects of the important parameters and experimentally verify how they affect the phenomenon. So, as I said, we think that the reporter only did a partial fulfillment of the task, since they didn't fully explain the parameters, control variables, and theory. And for the theoretical analysis, they talked about the structure of the screw and the XY plane rolling cone motion and the inclined plane rolling. And for their experimental confirmation, they gave experiments of the angle, size of the screw, and friction of the slope. So next, about the pros and cons of the experiment, of the reporter. So for their theory, they had a good theoretical considerations. However, they could improve on the qualitative explanation of the phenomenon, since they didn't give a qualitative explanation and didn't explain why the friction drives the phenomenon. And the contraction between the clash between theoretical and experimental verification is that they had no error investigated, and they have the lack of analysis and theoretical matching. And they only show the diagram but have no further explanation. And for the experiment, they have sufficient experimental data. However, they could improve on adding more explanation to their data analysis. And they could explore more on parameters as, for example, the length of the plane, the diameter of the screw, and the ratio of the mass between the head and the tail. And for the opponents, their pros is that they had clear thoughts and questions, identified merits and flaws of the presentation, and extended further discussions on the parameters, for example, the friction and size of the screw and inclined angle. And they identified merits and flaws of the presentation. And they could further investigate a better way to release the screw and the ratio of the mass between the head and the tail, and the contact area between a cone and a screw. So next, about the discussion analysis. The opponent asked a question that there's a weird peak in the data, and it can possibly be caused by hand-releasing screw. And the reporter said that it doesn't affect the result, as they have done it many times. But we disagree with this reporter. We disagree with the reporter because there's error created in the experiment and should be accounted for and should not be ignored. And secondly, they talked about, the opponent said that there's a better way to reduce error. And the reporter's explanation for that is that they had a high amount of experiment and that could reduce the error. But we disagree with the reporter because more experiment with the same error created does not mean it will reduce the impact of the error and it has on the experiment. And lastly, the opponent raised that there's an inclination of one of the boundaries of the experiment. And the reporter said that a larger inclination of the screw will slide. And we partially agree with the reporter because if the gravity force is... Okay, thank you.
2 minutes for the reviewer.
Okay, thanks to the opponent and reviewer. And let's to conclude. Yes. in our experiments, the larger inclined angle is shorter, have shorter periods, and the longer screws will have longer periods. And shorter screw large angle will flip, and small friction coefficient will slide. And the periods formula here, it's when we increase the phi is the inclined angle, the periods will decrease, and the edge is the length of the screw. When we increase it, the periods will be increased. Okay, and the opponent said we can use electromagnets, but I think if we use that, it will also affect the motion because we'll also have the velocity. Okay, in our discussion on the blackboard, the gravity is here, but it can just the period of oscillating, because if the normal force is decreased, the slide down force will increase, so the screw will slide down more.
Okay, time's up. Questions from viewers?
So can you play the video where the big jump is that we were just fighting over one other one? That can you play that video? How was it moving? And so corresponding to the figure that you plot, that you have a theta over.
This is the video just now is 50 degrees, and we can see the screw is slide down, and the amplitude of the oscillating is also decreasing.
Yeah, and so can I ask the opponent, why do you think that why do you think it has something to do with the releasing error?
Because if we use the hands to release, the hands might not be able to control the releasing angle very well. And the initial condition in this experiment is very crucial, because if the releasing angle increase about like 10 degrees, after a few of the oscillation, the oscillating angle will be totally different. So we believe this is the reason.
And just now the reviewer say that you agree with the reporter, and what's your point?
I said I partially agree, because if the gravity force is large enough, it should make the screws slide. But if only if the gravity is large enough. So we only agree only a part of what you said.
Okay, thank you.
Thank you.
Judge.
Judge. Judge.
Next day. I had Judge. 分数。就要等他们。
好，那我去顺便拍一下。
安达我拍
This your score. For the reporter, okay. Reporters.
446.
Opponent.
Wait. Is it 44655? Okay.
Yes.
Okay.
Opponent.
98877.
Reviewer.
Seven 78765.
Okay, let's conclude our first part of this session. Let's take a 10-minute break. So we'll return here within 10 minutes.
We would like to challenge question number 12, rice cannibals.
1 minute for the reporter to consider.
他们接不上。哪一台？你的那个。你们解析度有1024。
Okay. 5 minutes decoration time for the reporter. You write down the names of the presenters for each team.
虚粉，然后603一样是。这个差，这个差。我自己没有这样，没有说没有在这里。
Okay, the reporter has 12 minutes to present his work.
Honorable jury said all of the competitor, and the reporter continues Celsius, and today what I'm going to report is problem number 12, rice panel bills. And here's the problem statement. Pack a vessel and pour some granular material into it. For example, rice. If you dip a spoon into it, then at a certain depth of immersion, you can lift the vessel and contain by holding the spoon. Explain this phenomenon and explore the relevant parameter of the system. And the reporter will focus on what the force acting on the system and find the certain depths at which the phenomenon occur and how the different parameters affect the boundary condition of the system. And here's the reporter's outline. First is preliminary experiment, including the observation video and the quantitative explanation. And next is about the theory part. I will show you my hypothesis, Jensen effect, a picture of force diagram, boundary condition, and a certain depth. And next part is the experiment. I will introduce my equipment and setup and try various parameters such as radius of the rod, friction coefficient, and the mass of the system, and try to analyze the deviation. And last is the discussion, including I want to prove the assumption. And finally, is the conclusion. And here's the preliminary experiment. Here's the observation video. You can see that when we immerse the rod in a certain depth and lift it, the container will be lifted together. So in this condition, we define as a stuck state, which is the problem statement has mentioned above. But however, in the right video, when we lift the rod slip out of the vessel. So in this condition, we define as a sleeping state. And here's the quantitative explanation. So as the depth of the object increases, the pressure will also increase. So we can derive the total friction from this formula. And because the friction will offset the lifting force, so the rod won't come off the vessel. So in this condition, it's a static balance. And next is about the three kinds of explanation of this phenomenon. So first is that when the lifting loss T remains equal value. So and the friction between the rod and the particle equal to the weight of the container and the particle. It reaches the condition of static balance. However, when the friction cannot bring in the weight or the lifting force of the system, as well as when the system has an acceleration, the kinetic friction happens. So there's two kinds of conditions called the phenomenon won't happen. And next is about the theory part. First is the hypothesis of our theory, which is including Jensen effect. First, we assume that the vertical pressure is a constant in the same plane, and the horizontal pressure is proportional to the vertical pressure, and the density of the particle is a constant. And here's the theory of Jensen effect. First, we focus on the certain layer in the container, and this layer will be balanced by the normal force and the friction. So we can write the equation to describe this situation, and then substitute the hydraulic radius into the formula. We can get this. So by solving the equation, we can get a solution of vertical pressure and horizontal pressure, and it will be look like this. And by integration, we can integrate from zero to h, which including the mass of the container and the particle will equal to the friction between the rod and the particles, and which is the phenomenon happens successfully. So by rewrite the equation, we can get a certain depth of immersion, and this function is lambda w function. And next is about the boundary condition part. When the lifting force is bigger than this value, the slipping states happen, which is the phenomenon cannot happen. And since that we know the contact area is not continuous, so we use so we do an experiment to modify this problem by spray some ink on the rice, and we can cover with the rod. So we can get a value of beta, and we can find that the value is close to 0.73. So it's a constant in our experiment, in our theory. And next is about the experiment part. So here's our experimental setup. I use the clip to control the immersion of the depth, and use pulley apparatus to do the experiment. And I use the force meter and weight to ensure that the lifting force is a constant. And here's our analyzing method. So when we pull out the container successfully, we mark a circle on the graph. However, with the rod slip out of the vessel, we mark a cross on the graph. And next measurement is about the friction coefficient. So since that the particle will rotating on the inclined plane, so we stick them together. And find the angle, just let them start to slide out. And the tangent theta is the friction coefficient of between the particle and the inclined plane. And these are results of the experiment. And the first experiment that we conduct is we change the friction coefficient between the rod and the particle. So you can see that the friction coefficient has a negative correlation to the depth of the immersion. It's because that we control the total mass of the system, and the lower friction coefficient require a deeper depth to reach the stuck state. And you can see that there has some overlapping area, and which means that it's a form of the error bar in our graph. And this experiment is about we change the mass of the system from 200 gram to 800 gram. So you can see that when the mass increases, the depth also needs to be increased. It's because that a larger mass requires a deeper depth to reach the stuck state, so the friction can balance the mass of the system. And this experiment is about the radius of the rod. As we know, the radius of the rod will affect the contact area between the rod and the particle. So a shorter radius of the rod requires a deeper depth to reach the stuck state, since that the friction from the rod is small. So it has a negative correlation to the depth. And next discussion is about deviation analysis. As you can see, in the final part of the graph, the rice grains on the top layer are loosely arranged. So the beta, in the actual situation, the beta will be smaller than 0.73. And the rice grains on the bottom layer are closely arranged. So the beta will be bigger than 0.73, which is called the deviation in our experiment. And next discussion is about confirmation of our assumption. I want to prove that the vertical pressure is a constant in the same place. So I used a 3D printing model to stuck in the bottom of the container and measure the weight and felt like it almost the same. And next discussion is about, I want to prove the horizontal pressure is proportional to the vertical pressure. So since that in this condition, we only can assume that all the particles stack closely and the shape is the same. So we can know that each particle will balance by the friction and the normal force. So we can rewrite the expression like this, which is separately can be described as vertical, horizontal, and the torque. So by solving the equation, we can get the value of normal force and the friction, and substitute it into K value. So we can know the K will approximately equal to this, since that we assume that is closely arrangement. And next discussion is about the comparison between the rod and the spoon. So the difference between the rod and spoon which are the direction of the friction from the particle are not totally the same, and the spoon has a larger surface area than the video shows. And so in this discussion, we calculate the thickness of the spoon and use the same principle to calculate the vertical components of the friction, and the result will be like this. So when the weight of the system equal to the friction from the spoon head and the friction from the rod, it causes a steady balance situation. And this discussion is about we use the spoon to do the experiment as we change the mass as a parameter. So we can get the same result when same as the rod. When the mass increases, the depth also needs to be increased. And the deviation is come from we neglect the thickness of the spoon, and the direction of the friction is not totally the same. And this graph compares that in the same test, because the spoon has a larger surface area, so it can provide a larger friction. And this discussion is about the Jensen effect. We can know that in the final graph, the pressure will remain a constant, but it's because that the particle has a downward trend due to the gravity, so the steady balance will be upward. So the gravity will offset in the final section of the graph. But however, in our experiment, the scale is small, so we can ignore the effect we can ignore the influence by the Jensen effect. And it's a conclusion. First, when the lifting force is equal value, and the friction from the rock and the particle equal to the mass of the container and the particle, it reaches the condition of steady balance. And this formula can calculate the friction from the rod and the friction from the head. And this experiment is the conclusion about the experiment. So friction coefficient has a negative correlation to the depth as well as the radius of the rod. And the mass has a positive correlation to the depth. And the deviation is come from the difference of beta, which is the fitting constant in our theory. And this conclusion is about the discussion. We successfully proved that the vertical pressure is a constant in the same plane, and try to approach the K, which is the proportional constant in our theory. And the K will equal to this. And this is the conclusion of the spoon experiment. You can see that here has the same result as we change the spoon as a parameter. So the mass increase, the depth also needs to be increased. And the deviation also comes from we neglect the thickness of the spoon and the direction of the friction from the particle are not totally the same. And in this graph shows that in the same depth, the spoon has a larger friction because it has a larger surface area. And this is the conclusion about the Jensen effect. Since that, it is because the particle has a downward trend due to the gravity, so the static balance will offset the gravity. And so in the final section of the graph, it will remain a constant. But our experimental scale is very small, so we can ignore this effect in our experiment. And this ends of my report. Thank you.
2 minutes for the opponent to address questions to the opponent.
I
I'm sorry, but can you explain the Jensen effect more clearly?
Oh, since the Jensen effect is we consider each particle pressure, and like you can explain this.
Yeah.
Oh, because the Jensen effect is a effect that can describe the friction when when you want to calculate the pressure, but there's some friction from the container, so you may use this Jensen effect. Do you want to listen to the theory part?
Yeah, sure.
Okay, so since that we also can focus on the certain layer in the container, and this layer will balance by which is the normal force and downward force and the upward force, and that will be formed by the normal force, which can form by the normal force and the friction. And by derivation, we can get a solution of pressure vertical and the pressure horizontal, and we can find that it's potential function.
So I like that. How do you, wait, I don't know which word is,
Do you want to hear more about that?
I think that's it.
3-minute preparation time for your opponent. Okay, reporter has 1 minute maximum time to discuss his thoughts, followed by the discussion with reporter for a total of 14 minutes.
So yeah, the presentation is still I don't understand, but I will just ignore that. So basically, in a problem we're focusing on the friction between the granular material inside the tube and the rod. So the reporters they want to try to observe the boundaries of what would create a circumstance, and they use the density theory to theorize the way this effect works. And then they use the circular process of the different data to determine and find the fitting curve. And finally, they discover there's not really that much difference between their experiment and what they expected. And some of the good things about their presentation is first, in the theory part, they have a very detailed explanation and had they have thorough explanation of and good theoretical considerations of this effect. And during the experiments, they have stable experiment setup and they very many key parameters, and they have also sufficient experimental data and a lot of theoretical verification. And also in their presentation, they have very good diagrams and visualization, which makes the entire presentation a lot more clear. Yeah. So here are like basically some of the discussions I would like to discuss with them. Like first is about the density section, how the weight makes you sure that the density is always at a constant value, and also how the angle, like if they've ever think about the different angle that will create different results, and also find how the x-axis is determined in a graph. Like these are some of the discussions I would like to discuss with them, basically. So that's it. So I just like
Sure, go ahead.
Right. So first I would like to ask about the density, like because in your presentation you said you use the weight of the density. Then you use the weight of the density to determine if it's a constant density. But I mean, like how do you use the weight to determine it's a constant density?
We calculate the average density in our experiment that we conduct.
So right. So like I would suggest like you could do a more like I can actually reword that question. Like how are you sure that your density each time the density you do the experiment, the density you use is the max density that the material could possibly use?
I think because we control the average particle density in our experiments, and we found that the deviation come from this is very small, since that is almost a constant in our experiment, and I think that it won't affect a lot.
And as a fun, we believe that to gain the max density of each material, you could like do some vibrations. I mean, you could do some vibration onto the granular material to make sure it's all half density, and to make sure it's at a max constant density that you could do experiment with. Yeah. And also, secondly, I would like to ask that: did you ever think about the size of the particle?
since that we use the rise, which is the promise statement mentioned above, so we didn't change the particle in our experiment since the promise statement has been used like rise. But I think that the size of the particle will affect, which is affect the beta in our experiment because when the size of particle is big, it might the contact area between the rod and particle might be smaller.
Okay. There's also a question about the fitting curve that I would want to ask.
Sure.
Yeah.
Which page?
I forgot. It's like 20 something.
This one?
Yeah.
Okay.
Like I would like to ask because like you only did maybe like 4 different friction for different experiments. So how are you sure that this fitting curve is
You can see that the
correct one?
trend of our series line fit the experimental data, and the experimental error between each data point is very small.
I could see it has only a very little difference in some of the data. So are you sure it's because the fitting curve is not curved, or it could be some other?
I also mentioned that in the report that the main reason of the deviation is come from the fitting because we cannot ensure the actual situation that the arrangement in the arrangement of the particle in the container. We cannot ensure that, so we only can use fitting method to solve this.
Okay. There's another one I would like to ask. Have you ever thought about the angle of the spoon or rod will change the result of this experiment?
You think how do I ensure that the angle is 90 degree or?
Yeah, like is the angle of the rod one of the variables that we could discuss?
So we use clip to control and measure the angle between them is 90 degrees, and use camera to take a picture and find the angle.
Okay. So I would like to ask do you think that this angle could be a variable that
yes, I agree, but we didn't do the parameter about it.
Okay. So can you because in the end you said that the Jensen effect the Jensen theory won't affect that much won't have a big effect, huge difference on the effect of the result of the experiment. So can you explain
Since
how
that the experimental scale is very small, so it's only including this part, and we also do a experiment to ensure that the Jensen and to ensure that our theory is correct.
Okay.
And in the final part of the graph is because you can see that it has 4 meters. So, but in our experiment, the scale is very small, compared to the 4 meters. So this part of the graph won't affect.
Why do you choose to use a rod at the beginning of your experiment?
Since that the rod is easier to consider. And the promise statement has also mentioned like holding the foot. for example, take an example for holding a spoon. So I think different object might be an important variable or parameter that we should conduct in our experiment.
So there's a question like, have you taken into account the density of the material when you calculate the surface area?
Because every time the rod, because the density of the rod in our experiment won't change. So I think we should only measure the average density of this system, like on container and the container and the particle. And so in your PowerPoint you have mentioned that we have no quantitative explanation, but
I'm sorry about that. Sorry. I would like to ask about one of the other possibilities of this experiment, like because in this experiment you only mainly discuss about when the speed when the velocity is at a constant. So what do you think would happen if we added an acceleration in the velocity?
Oh, it's because when the acceleration is big, it might cause kinetic friction. Which means that we will decrease the friction between the rod and the particle. So I think it will complicate our problem.
So do you mean that you think if it has an acceleration, the result will be entirely different from what you.
Yes, and the problem statement has no mention that we must use acceleration system. So we only consider when in a theory part we only consider the lifting velocity remain an equal value, which means that this is a steady bed system.
I think that's probably it. Thank you.
One minute summary time for your opponent.
So in the result, the reporter did a great job at describing this question. They have described a lot of the variables about this question and about how they would interact under different circumstances. And finally, they also given out a sufficient proof about why this experiment ends up in the effect that it results up in. And this is a really learning experience, and it's very, I don't know, yeah. Thank you.
Okay, reviewer, these texts have a lot for 10 minutes.
I would like to ask the opponent, so what do you think is the main parameter of this experiment and theory?
Oh, I think we think it's a friction in between the primary material and the rock.
Okay, reporter, main parameter.
Main parameter, I think the radius of a rock, friction coefficient, and the mass of the system. Both of three of them is the important parameter.
Okay. So next page, please turn to 24. So
24.
Yes. So in page 24, that there's many positive deviation of your graphs in experimental. Yes. So could you explain it and say the same in page 36? Yeah.
It's because the difference of beta. Because we cannot ensure the actual situation in arrangement situation in the container. So we believe that it's caused by the difference of beta.
Okay, so which is another comment? Did you think the arrangement affects this phenomenon, the positive?
Can I ask again?
So this is about the positive deviation of the graph. So did you agree with the reporter?
Yeah, I agree.
Okay, so next question. In your theory of reporting, in the theory of the spoon, you say that you did an integral, right?
Yes.
Yeah. So, but if the rise is too big, so is it discontinuous in the spoon?
So I use the fitting constant to modify this problem, since that its beta is which equal to the rate of the actual contact area and the theoretical contact area.
Okay. Did you agree with that? Did you think this is reasonable?
Well, I think it's a reasonable graph.
Okay. This question. So the density of rise, did you consider the volume in the actual volume or the container volume?
We calculate the average value, which is when we measure the container with full of rice, and we calculate the average density in our experiment.
Okay, so which method do you think is more reasonable? Which method did you prefer by measuring the volume?
What do you mean by which method?
Okay, it's okay. So next question.
Okay, time's up. Review has 2 minutes to prepare. Okay, 1 minute for the reviewer.
Okay, so thank you, opponent and reporter. First is the problem statement. So in the problem statement, the reporter talks about the key points of the certain depth and listing, and they want to find a relevant parameter. Okay, so there's a pros and cons. For reporter, the pros is that there is clear experiment setup and there's many deviation analyzed, which is very good. But the cons is that just skipping the slide too fast with too many equations, which the opponent couldn't comprehend it fast. And there is no quantitative comparison between the theory and the experiment. So the opponent
just ask the direct question, which is good because the reporter just slides these too fast. But sometimes the opponent just didn't comprehend the theory and keep using times. So in the question of discussion, so first one, the opponent asks, so how are you sure that the density is constant value each time? So the reporter answered that they use average density. So and they just analyze the deviation. So we agree with the opponent. More. Okay. So the opponent asked, did you consider the size of the particle? So the reporter just answers, they think the size of particle will affect. So in my opinion, we think that reporter is right. Okay, so the next question the opponent asks, so about the method they control the angle of spoon is the same every time. So the reporter is say they use camera to take a photo, but I have some question about how do they take a photo in the rice pile. And next question, the opponent asks, so why did you choose raw to do? The reporter says the problem statement mentions the raws, and also we think the object is a parameter to discuss. So we think that reporter did it right because in problem statement the phenomenon is more important. So choosing an easier object is very good. Okay, so the reviewer questions. So first one about the main parameters. So opponent answer that is friction, and reporter answers is the friction and the coefficient, which we think the reporter answer is more complete. And so the next question about the theory that you assume the particle is the ball pit in your experiment. So the reporter just says that they do some analyze and coefficient correction to the theory, and we think that the reporter did it very good, and the opponent also agreed. And the next question about the actual volume, and the reporter says they calculate the average density. So how we suggest that you can measure the actual volume and the container volume both. Okay, so that's all.
Concluding remarks, if I recall, 2 minutes.
And first, here's my concluding remark. First, we have defined that the stock state, and also we have the quantitative explanation in our reports, as I mentioned. And we have theory line for each parameter, and it matches the trend map the experiment very well. And we use the fitting constant to analyze the proportional of the proportion of contact area, since that we don't know the actual arrangement of the particle in the container. So instead we use the fitting constant to modify its problem. The spoon has a larger surface area which caused by the larger surface larger friction. And the Jensen effect can be used to calculate the pressure in the frictional container. And we also control the particle density in our experiment, and deviation is caused by it is very small. And I believe that because all the container in our experiment is the same, so we just need to consider the average density. And we also measure the particle density and found that it won't affect a lot. And since that each particle the shape is different, so we can only calculate the average. And when the acceleration is big, the kinetic friction will happen. So we didn't do an experiment about it, since that it will complicate the question and complicate the problem. And the size of the particle will change the value of beta. And we also control the insert angle of the spoon at 90 degrees throughout every experiment, throughout the experiment of the spoon. And the experimental scale is very small, so the effect of Jensen effect is really small. And the deviation is mainly caused by the fitting constant, which is the beta in our theory part. Thanks. thank you. Here's my concluding remark.
Thank you. Questions from viewers?
All the people. You mentioned that the pressure. So the pressure in a fluid. What is the difference between the pressure in the fluid and in your granular particle? Are they different? How can it be different? Or they're just the same?
First, okay.
Pressure for your granular particles or pressure for fluid like water. Are they the same? What's the difference?
Because when the
Just a difference. Are they the
difference
same
in
or?
a frictional container, because the friction will offset the gravity of the granular material.
So what about the fluid pressure? Just short answer.
The viscosity from the between the friction between the water and the container is very small.
Yeah. Yeah. Opposed.
I think it's mainly at the friction part.
Okay, so I think it's like continuous or not in the main that affects the most. So because in the rise that the contact area is not continuous, but in fluid it is.
I got a question for you. Before that, is you going to page 21 with the formula for the pressure? Yeah. The PY. Could you tell me what is the H? H is the depth, right?
Yes.
And if H is the depth, then the PY is going to go saturate as H goes deeper, right?
Yes.
And why is that? Because this is going to be something that related to the question.
Because after integration, the solution of this will be an exponential function.
Well, I would expect that even if you go deeper, you have more materials on the top.
Yes.
The water is going to saturate that.
Because the friction will offset the gravity.
And have you tested this?
We didn't test it because the experimental scale is very small.
Okay. What about component? Your opinion?
Well,
That's fine. If you have comment, you review it.
So I think the report I partially agree with the reporter, but I think that it needs experimental data to prove it.
Okay. Thank you. Okay. The reporter, please show the floor for the reporter.
89876. Opponent. Five, 4, 5, 5.
And the reviewer.
Six, 7, 6, 5, 6.
Okay. Shall we take a 10-minute break? Okay. Should we start now? Take your seats. Okay, opponent, you have 1 minute to propose a question and problem for the reporter.
Okay, team, maybe we would like to challenge problem number 2.
Problem number 2.
The also oscillate here.
Okay, problem number 2. Write down names on the blackboard, please.
什么？没有，等他们下一个阶段我再去瞧。好的，别写，不写。
Okay, reporter, please take the floor. You have 12 minutes to present your work.
Hello, judges and fellow physicists. Today I'll be talking about the problem statement oscillating spheres. And we are a team effort. So first, I will have to address the problem statement. Well, our main focus on the statement is the ball needs to be rotating beforehand, and then it needs to be conductive, which aside from the conductive ball, the conductive sphere, you need to suspend it with a non-conductive material like a wire, because in the problem statement. And plus, from the problem statement, we can see that if we add a magnetic field, it will influence the outcome of the results, no matter is it the period or the amplitude of the velocity. So this should be a video of the experiment. And first, from the video demonstration, we release the ball by hand, and of course people will say that it will cause a little bit of error. But from that standpoint, I will say that originally we are trying to use a motor, because motor spins it can be controlled how the revolution per second. But because of the motor spinning too fast for too many times, causing the wire to usually come off the sphere, which will cause the experiment unable to continue. And from the video, we can see that we attach a black plate on the sphere, and we added a cross. It's because we wanted to track the motion of the cross to know the velocity or the position of the x and y axis at every time. And our theory is mostly about eddy current, which eddy current is mostly talking about if there is a conductive surface and it's featured with a magnetic field, then the gradient in the magnetic flux will cause eddy current to be formed. And the form of the eddy current is used to oppose to the change in the magnetic field featured by the environment. So from the picture, if you can see that if we're putting a magnet with an end pole next to the conductive surface while it's spinning, it will after the area close to the magnet, after it passes, the magnetic flux will feature a decrease, which will cause eddy current to form from this theory. And when the eddy current forms, it will be in a certain direction to match up to the loss of the magnetic flux, which as the after effect is it will also create a magnetic field, which in that case it will be an attracting force will try to stop the ball from keep spinning. And if the ball spins faster than the force, of course it will spin over. But after many times of this, because we can take many different areas from the conductive surface, and after that means it will feature a lot of attraction at the same time, and it will cause the ball to have a decline in the speed. So, and if it is on the other hand, we can actually see the same phenomenon happening. But the only difference is at the end, it will cause opposing magnetic flux, and it will cause repulsion, which will also stop the ball from spinning. So our experiment setup is a ball roll with copper tape, and of course we all know that the aluminum tape is also available. But copper being a much more conductive surface, we decided to use copper tape so to make the results more clear or observable. And then we use a wire that's non-conductive. Usually, at first we use a copper wire, but then we use a non-conductive wire, for example, like a string, to connect the sphere to the stem. And then we will have magnets, and we use the same magnet out of the same pack, which means that it will have roughly or estimately similar magnetic fields will be generated from these magnets. And then we will of course attach a black cord onto the ball to track the movement. So from here we'll be talking about the variables that we will be introducing. So the control variables is of course very obvious. It's of course the same sphere, same magnetic field, and the same sphere, same wire, or at least the same amount of revolutions every time we spin the ball. And the independent variables we're talking if, for example, if we feature two different magnets, it could be n to n, which is the n pole faces inward, or we can feature an n and s, which will feature an n pole at the sphere and an s pole at the sphere on the other side. And the dependent variable that we'll be mostly looking out for is the decline of the period it takes to finish one revolution, or the decline in speed as well. So our data analysis mainly looks something similar to this. So the red one. So first I have to introduce the two axes. So the x-axis is the time, which will be seconds, and the y-axis is the velocity, which is meters over seconds, and the y-axis number should be times 1,000 because the graph is made this way, and every graph featured on like this will have the same x-axis, which means the same amount of time featured, and the same height, the same difference in the different y-axis numbers, which means the graph should be, you can stack the graphs up and actually see some difference. Well, I'll be talking about that further in our presentation. So then we are talking about if we have two magnets, which if we feature two magnets, we can either see it as n pole and n pole, or n pole and s pole, which of course the graph it will actually of course show the same thing, the velocity and the time, the velocity at different times. And people might be wondering why would there be spark dots, because the lack of engineering, we use the most formal way of tracking the dots. So we use tracker to track the dot, which sometimes because of the cost for being drawn too big or too thick, it will cause the dot to not be on the dot to actually be in different, not be in the spot that we want it to be. So it will be tracking maybe the side of the cross, or maybe outside of the cross. So it will cause speed to increase drastically, which will cause spikes. But I will be excluding the spikes from in the future analysis. So the first is the data analysis. If we look barely off of the thing we got from the tracker. So first, it wasn't very clear that it used to not be very clear why the four graphs were so similar, because they have the same period and they have almost the same similar decline. But I originally assumed that it is because the magnet being too weak and causing a magnet not able to produce such a magnetic field, and it cannot affect the phenomenon as severely or as effectively as if you have a stronger magnetic field. But from the next page, if we break down the dots and track every single dot, every single peak of the velocity, which means the max velocity at every revolution, we can see that there is a decline. Of course we can see decline in the velocity of the peaks. But what I most wanted to talk about is the first decline, which means from the first row to the second row. And the first row to the second row, we can see that if we have no magnet, which is the top row, if it is at the far distance, which is 5 centimeters, you can see that the first decline is roughly the same. Which I will explain it is because of the magnet not being strong enough to produce a magnetic field over 5 centimeters to affect the phenomenon. So that's why they have similar results. But on the other hand, we can see that if we are at 1 centimeter, or we feature two magnets at the same time, despite the different poles faced at the sphere, it will produce similar results because of the eddy current theory. It will cause attraction and repulsion forces to cause the ball to stop more, to have a decrease in velocity because of the forces. So our conclusion for this is first, is in theory, or the eddy current theory, we suppose that a stronger magnetic field will cause a much more observable eddy current, or a larger gradient in magnetic flux, which will cause eddy current to be stronger, and the eddy current will also stop the ball from oscillating because of the actuation and repulsion, which we can see from the experiment. And secondly, what we're talking about experiment is that the more magnets and the closer the magnet is to the ball, the decline will also be faster, which will feature a much faster decline from if we look only at the peaks. So that is mostly part of my presentation. Thank you.
Yes. Can you tell me if the magnetic force is not discharged with the gravity? Because you think the magnetic is in a horizontal,
yes.
Yes. But if it is not.
You mean what if it's not in the horizontal axis, it's on the vertical axis? Or
have a theta.
Oh, you mean there's okay. So to that, I think that even though we have a lack of experimentation, but I can predict that if we added a theta into the play, it will continue. If we add a theta, it will of course, according to the theory, it will stop. It will not only create a stop, but the stop will have an angle as well.
Okay, and then can you tell me the charge difference?
You mean what?
Because you said the magnetic field is too small to influence this. So, but this question is to ask you why how the magnetic field to influence this field, but you say it's not influenced too much.
I think you misunderstood a little bit of my presentation. It's because I originally thought it was because it's too small, but actually you can from the diagram you can see that there is still a difference in the design, as I said before. That means that the force might not be as obvious, but it is still present in my statistics.
Okay, and another resistance
Here, time is up. You have 3 minutes to prepare for the next 16. Okay, opponent has a maximum 4 minutes to present his idea, followed by the discussion with the reporter for a total of 14 minutes.
The problem statement is that here with the conductive is something where and when the sphere is rotated around its vertical axis and then with this is starting to offset. And the topic main idea is to talk about the magnetic field by how to influence this sphere. And I think the summary of reporter using has to receive the sphere. And the first is clear show the phenomena, but I think the reporter lack of the theory. Can I don't know you know this this phenomena is which motion is, and I think this is the damping solution. And can you describe what is damping solution and how to influence in this yes. And the wire the process clearly shows the parameter, but the concept makes discussions of the parameters. And I think in the eddy press the word in the theory is planational photo is too small and not explanation of the theory. Yes. And because I think this is not only force on one side is around this sphere. It's not influence in one side. Yes. And the reporters using compact magnetic wire and a blackboard to set up. And the first is lot of I think the photo is not clear enough, and the axis isn't clear, and I think the theory is not enough. Yes.
Next stage. Truman.
I think the summary of reporters quantum magnetic field also. I think
Go to the next step, discussion.
yes.
Okay.
Sorry. Can you tell me some theory about this?
Theory.
Yes.
Because you mentioned a lot of times about the damping solution, but I think although this is part of the theory, but I think you contribute to because by my perspective.
So quick, what theory about this?
I think both should be included. I think damping can solve it can be a part of this phenomenon.
Also, can you tell me which of the damping is this question is under damping or critically damped or over damped?
Can you say?
Under dense, critically dense, or over dense. Which of these questions?
Because of the lack of information on damping that we didn't do, because I thought it should be something about eddy current, but
so you think this? So you don't know which of the damping in this question?
Yes.
Yes, and I think the current flows in this sphere ought to its flows in this sphere.
Can you say it in much more fluid manner?
Can I use blackboard?
Sure.
Because this is the sphere, and you have the magnetic field to influence this, and how the current flows on this top.
You mean how the current flows?
Yes, yes.
Or maybe because of the maybe because of
And
pictures.
And can you tell me how the because if how can you turn to page? Yes. Next. Yes, yes. Can you tell me?
Oh, okay. So this is if this is a conductive sphere, and we feature a magnetic feature, and then we can see that this is the power button. So if we look at the sphere, right? If we like the sphere is round, and if we look at this axis, so we slice it like this, we see it from this axis.
So you only influence here?
It might have a larger influence, but I'm just looking at small parameters for easier for explanation. What do you mean?
So all of this will, but this will be
In what?
will not only have negative or positive. It will combine its
Combine what?
Negative and positive stuff only does. And here, what is it?
What do you mean how the positive effect?
Yeah.
I didn't because my theory is talking mostly about the current, so I didn't talk about the proton or the electron or the particles that are electric.
But I think in my opinion, this will be the field here, and here have a magnetic field to influence this, and here have a wire. Yes, and can you tell me if here is the current is to spin like this or spin like this to influence this.
Can you rephrase because you kind of oh sorry. Okay, you mean the voice?
Yes. And when it's in, okay, you can describe how you think.
Okay. Because you mean how I describe?
Yes.
I think being either one will affect the field.
Okay. And how this, because you need to spin it first, and
Yes.
You will, and how you think it first to do. You in the start. This, because you need to bring it and okay. And okay, next. And can you find the difference both of them? Both?
Between them. Yes, because firstly, I know you're talking about damping theory a lot, but from my perspective, I think maybe you're not wrong, but I don't think you maybe have made. I'm not sure if you know eddy current or not, but I think it has some relevance to this problem as well. But of course, I won't exclude.
So you not very agree this is a damping solution.
Of course, I agree this is a part of the damping solution, but I think but I look at it from this perspective because I'm looking at the decrease or the decline of the velocity. I'm not looking at I know it will change the circular motion or it will have its own damping motion, but I'm not looking into that.
Maybe if you think this is damping solution, but I think this maybe not is influenced by magnetic field. Maybe it's from air, some resistance.
But I have to explain that because I actually did it without magnetic field and with magnetic field, and I see a difference between them. So that's why.
Maybe it's the air
but
difference.
I included the one with magnetic field and one without.
Yes, but I think because your influence is not very big, it's influenced a little, so I think maybe it's just influenced by the air.
But both will be influenced by the air. Because no matter if we actually added an external magnetic field to it, I think that if they both won't actually, they will both feature air resistance.
Okay, and I think your is too small. I can very.
Because this is not what I'm mostly going to talk about. That's not the most important thing. But mostly from
this is not the important thing.
Well, from this graph, I didn't.
What you did, what you want to think about this question?
Okay.
Because
can you let me finish?
Okay.
So firstly, I know maybe saying this as irrelevant or important might be discouraging, but from this, I want to tell you that there is a decline in the velocity. Yes.
Next page. And this is describe again.
It is a decline in velocity. Thank you.
And why this is your chart is very big and your is only very small and too small to look.
Oh, if that's the problem, then of course I could adjust in further experiments, but I don't think that is relevant to this problem.
And compare them. Four chart.
For what?
Compare four chart.
Okay, with four chart. We mean
chart.
Oh, we compare the four chart. I did compare it in my that later. I did compare how for them with the ones and without. This is the main chart. Like I take it down to this.
Okay, and because your magnetic field is not very big now, right? It was not very big.
Not very big.
Yes, and how you will to improve your advertisement
What?
your device because your device is not very well now.
What?
Not very well now because the magnetic field is too small.
Oh, but I overcome the lack of magnetic field by using a smaller.
Okay, time is up. We have to move to the next. Okay, 1 minute for the opponent to make a summary.
the reporter said he used this chart, but I think this chart is cannot to look a very good, very thin to look because I think the influence is also too small, and I think you only need to change 1 centimeter, 5 centimeters, and yes. So I think the operational variable is too not enough, and I think he need to consider the kappa of the wire.
Okay, time is up. 10 minutes for the reviewer.
So for both the reporter and the opponent, what are the forces that act on a sphere without a magnetic field?
I think if you consider area distance and the torque of the wire to the
So the torque of the wire is the forces that cause damping. Okay, for
I think if there is not magnetic field, it's also a damping solution.
yes. So what are the forces that cause damping?
I think if the magnetic field to plus in this device, the damping solution.
What are the forces? Force.
Magnetic force.
And without a magnetic field.
Usually without a magnetic field,
Yes.
with force,
Yes.
the air resistance.
Okay. For both the reporter and opponents, can you do you think that a solid or hollow sphere could have a more significant phenomenon? Solid or hollow sphere?
I think hollow.
Hollow. Can you explain that?
It's because I think because of because it's hollow, and that means I think the decrease in mass will have
Okay.
effect.
Then for the
I think it's a hollow because if this is not hollow,
Okay.
it-
okay, thank you. For the reporter, if the magnetic field is parallel to the rotational axis, will it still affect the motion?
I think it will still cause a little amount of the damping motion.
So the magnetic field will still affect the motion.
Yes.
Okay. And do you think that the eddy current will only be on the surface, on the sphere, or also the inner part of the sphere?
I think if the whole thing is conductive, I think it will happen on multiple layers.
So multiple layers. So all of the layers will all have
Will all
eddy
feature
current.
eddy current.
Okay. And since you use copper tape to wrap the sphere to change the conductivity, can you explain why won't the uneven surface of the tape affect the phenomenon?
Why wouldn't it affect the phenomenon?
Yes, because the surface of your sphere is uneven.
That's why we try to make it look, because of course we could do it.
So
We try to make it as even as possible.
So it could affect the phenomenon.
Yes.
And do you think that by using an even surface could optimize the experiment?
Can you say that?
With an even surface, will it optimize the experiment?
Okay, time is up. So we have to move to the next stage. 2 minutes preparation time for the reviewer.
Oliver Drury's another competitor. I'm the reviewer of tin cells here. Today I'm going to review problem number 2, oscillating sphere. This is a problem statement. A light sphere was a conducting surface suspended from a thin wire. When the sphere is rotates about a vertical axis, thereby twisting the wire, and then released, it starts to oscillate. Investigate how the presence of a magnetic field affects motion. So due to the problem statement, we mainly focus on how does the oscillation act, and how will the magnetic field affect motion. And this is a review of the report. So the phenomenon is a damping with a magnetic field, and he used eddy currents in his theory. And in the external part, he used a copper tape, and a non-conductive wire and also a parameter of magnitude. And I believe that the reported lack of analysis on the forces like friction and air resistance without a magnetic field and also with a magnetic field. Also, he lacked a comparison of the experimental data and the theory since he introduced the theory. And this is a review of a position. So the first is that he noticed the lack of experiments about the magnetic field with an included angle. However, he didn't notice the uniformity and measurements of magnetic field in his discussion. And here are the key discussion of the opponents and reporter. So the opponent asked which kind of damping happened in this situation, and the reporter didn't give a clear answer to this problem. However, the reviewer believed that it's under damping since the trend of the oscillating angle is like a wave. And the opponent asked what is the direction of the current flow, and the reporter didn't give a clear direction of the direction of the current flow. However, the reviewer believed that the eddy current flow will make a circular motion here. So with a magnetic field flux goes through the sphere, it will create a Lorentz force like this way, which is opposite the rotating direction. And then we ask that what are the main forces without a magnetic field? And the reporter says it's a torque of a wire and air drag. And the opponents also believe that it's caused by air drag. We partially agree with this answer because air drag did influence the oscillation. However, the friction as suspension will also influence this oscillation. And it's also a main force that needs to be considered. And will the current flow only be on the surface or also the inner parts of the sphere? And the reporter believes that all of the layers will have current flow. However, the reviewer disagrees with that since only the surface of the conductive layers will have a current flow. And here are the points missed of both the reporter and the opponents. So he missed the uniformity of the magnetic field. Also, he didn't measure the magnetic field in the reporter presentation. Also, he missed the structure of the sphere, the thickness, the radius, and whether a solid or hollow sphere could affect the phenomenon. And also, he missed the points of angular frequency in his experimental data analysis. Thank you.
2 minutes for the reporter to make the
So to make some concluding remarks, I want to say that first, I think despite we think that our theory, of course, of course, we think that eddy current is always featured in when a magnetic field is featured in this phenomenon. So that's why we think that eddy current is a part of this theory. And second, I think I investigated some parameters, and of course it could be extended in the future. But we still did some about like for example of the distance of the magnet and the different placement in the magnet and how it affected phenomenon by using the eddy current theory. And thirdly, I think it interferes and I talked about the error results and about like no matter if you're turning by hand or about the uneven surface, and justifies the reason of the results. And to clarify, I think that in the start, we use aluminum disc at both sides, but because of the spinning, it will cause waves of electro like lightning to cause like a Franklin Bell effect, which Franklin Bell effect is mostly affected by electricity, which is not by magnetic field. So that's why in the end we use magnets instead of the disc that the opposing side is talking about. And after clarifying that, I think that's the end of my presentation. Thank you.
Okay. Questions from jurors? Okay. Thank you.
Thank you. Thank you.
Okay. Let's show you scores. First, for the important. Five, 7, 5, 5, 5. Okay. For the opponent, 4, 5, 5, 5, 5. For the reviewer, 9, 8, 8, 7. This concludes this afternoon's session. Thank you very much for taking part in this discussion.